In this podcast, we're going to be looking at instantaneous rate of change, but I thought we would start with a comparison of average rate of change and instantaneous rate of change. So average rate of change is the difference quotient, and it measures the average rate of change between 2 points. It's the slope of a secant line to a graph. Right? Difference quotient just means that you have a fraction. Right? That's the quotient part, and difference, you're taking the difference, the change in y divided by change in x. So your average rate of change is just the change in y, change in the value of the function, divided by change in x. If we want instantaneous rate of change, that's the limit of the difference quotient. So we take that, but we're taking the limit. And now the difference in our x coordinates is approaching 0. So instantaneous rate of change is the limit of the difference quotient as h approaches 0. That measures the instantaneous rate of change at the point of tangency. Right? So we're measuring the rate of change at exactly some point for our function. It's the slope of the tangent line to the it's the slope of the tangent line to a graph at the point of tangency. So instantaneous rate of change is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Right? So the difference in the x coordinates is approaching 0. And so we take the limit of that. So as we get closer and closer, so there's no difference at all, so we're right at a point, that limit there is giving us the instantaneous rate of change. The instantaneous rate of change of a function is called the derivative of the function at x. Right? So our derivative is our instantaneous rate of change. To find the slope of the tangent line of a function, we need to find the instantaneous rate of change of f of x. We need to find the derivative of f of x, and then substitute for x to find the rate of change at a specific point. Right? So if we want to know the slope of the tangent line at a very specific point, right, we simply substitute. So let's say our x value here is going to be a. Right? If we substitute that into our derivative, that's going to give us the slope of the tangent line, which is just the instantaneous rate of change at our point a, f of a. All right? So a little comparison there of average rate of change, instantaneous rate of change. The rest of this podcast and this lesson, we're going to be focusing on instantaneous rate of change. All right, here's a summary of the steps used to find the equation of a tangent line to a curve at an indicated point. So first we're going to find, and you have this in your notes, we're going to find the first derivative of f of x. So remember, you can put this in your notes. Probably good to have it right next to it. All right, so our derivative is the limit as h approaches 0, f of x plus h minus f of x divided by h. All right, it's the limit of the difference quotient. You're going to plug x values into the x value of the indicated point into f prime of x to find the slope at x. So once you find the derivative, right, so that would be f prime of x. Let me write that a little nicer. So once you find the derivative, then you plug in whatever your x value is. Right? So if your x value is a, you take f prime of a. That's going to give you the slope of the tangent line at that particular point. Right? And then you'll need the y coordinate. I actually need to write a little smaller there. You need the y coordinate, right, to for your line, right? So you need to know the y value that goes with that particular x value, and that's going to be the y-intercept for your tangent line. So you just plug into the original function, right? So now you just find f of a. Right? So f of a gives you the y value. F prime of a gives you the slope. Right? So I'm just going to point there. And then you just combine to write the equation in point-slope form. Generally, we're going to leave our equation in point-slope form. Sometimes we do a little modified version of point-slope form where we're going to isolate the y. But we don't necessarily have to simplify that to slope-intercept form. Unless the question asks for it, leaving it in point-slope form is perfectly fine. All right, so you substitute x into the derivative to find the slope. You substitute x into f of x to find the y for your point, because you need a y, not just an x. All right, so let's try with this one. First, we're going to find the derivative using the difference quotient. Ooh, look at that, a fraction. We can do it. All right, I'm going to write the equation for the limit of the difference quotient. You don't have to write it. It's in your notes. Enough times, I think. Oops. Silly me. I did not mean to make an h there. I meant to write an x. I meant to put an h right there, though. All right, so there's our formula. All right, so we have the limit as h approaches 0 of, and so now I just plug in the x plus h and the x right into my equation that I'm given there. All right, so of course f of x is just going to be the equation that you have, and then f of x plus h, you just substitute x plus h everywhere you see an x. All right, so this is going to be 3 times x plus h minus 3 divided by x, all divided by h. All right, this is an indeterminate limit. Right, that is an indeterminate limit. We need to combine the fractions. Right? If you were to plug in 0 right now for h, right, you'd get, so h would be 0, you get 3 over x minus 3 over x, that'd be 0, and you're plugging in 0 for h, you have 0 over 0. Right? So we know that's the indeterminate limit. We've got some factor, right, that's hidden and we can't see it, we can't find it, right, and it's causing us to have the 0 over 0 effect. Right? So we need to find it by rewriting this by rewriting our function here, our equation. And to do that, we need to combine our fractions. So I'm just going to move down here. So I have the limit. We need a common denominator as h approaches, oops, my arrows are kind of funky looking, 0 of 3 divided by x plus h minus 3 of x. All divided by h. We're going to change our denominator so we have a like denominator. Our least common denominator, you've got 2 separate factors there. So it's just going to be the product of those factors. X times x plus h. They're different. Right, so this one needs an x. Put an x in the denominator. Got to put an x in the numerator. This one needs an x plus h. Put an x plus h in the denominator. Got to put an x plus h in the numerator. I'm also going to give you a little suggestion here. Number one error in this problem is not distributing the negative. You don't think of it as negative 3. You just think of it as 3. And then you forget all about that subtraction, and only the first one gets subtracted, not both of them. So anytime in these problems where you have a subtraction, just change that to a plus and give this one the negative sign. All right? If you do that, you're not going to make the errors. Chance, maybe like 25% of the time, 10% of the time, whatever it is, you're going to forget to distribute that negative on the subtraction. You're just not thinking of that as part of the 3, and then your answer is going to be incorrect. Right? You're going to do all this great work, and then one silly little distribution error throws it all to pieces. Right? So just do plus and negative, and then you won't have to worry about that. All right, so back to simplifying. All right, so now I've got the limit as h approaches 0. My h is looking a little funny there, as h approaches 0. And we have 3x. And in the denominator, we have x times x plus h. And then we have, going to distribute the negative there. And we're going to have negative 3x and negative 3h. And there's really no reason at this point that we just couldn't make that one fraction, right? They're both going to have a denominator of x times x plus h. So we could write it twice as two separate fractions and then just combine to one fraction, or we could just do it all at once. And that's all divided by h. Very important because I've seen this error occurring. Just a little note here. This is one fraction, and this is the other fraction. Right? So this all goes together, right? The whole thing here from 3x minus 3h, x divided by x plus h, that's all one fraction, right? That was the limit of the difference quotient, and then we're dividing that all by h. Right? For some reason, students are wanting to make this a fraction, right? That's not the fraction, and they're flipping that one, and I don't know why. Right? That's not the fraction. Right? We're dividing the whole thing by h. Right? We're not dividing 3x minus 3h by x divided by x plus h divided by h. No, 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 no. X divided by x plus h, that's the denominator of that fraction. And for some reason, students are flipping that. And no, 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 no. All right? Don't do that. That's just wrong. All right, so 3x minus 3x, that's going to be 0. We're going to be left with a negative 3h. Almost forgot to write limit. Oh, and I actually forgot to write one other thing. Start a new video. Forget to write down that this is our derivative. Right? We need to include that, right? Because we're going to be finding f prime of 2. We need to make the connection that the limit of the difference quotient is our derivative, right? Yes, we know that's what it is, but we need to show that's what it is. All right, so now we're simplifying, so we have f prime of x equals the limit as h approaches 0, and that would be negative 3h divided by x times x plus h. That's one fraction, and now is a good time to just rewrite that divide by h as times 1 over h. All right, remember that. Right? It looks like that when we rewrite that as multiplication. It does not look like this. This is no, 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 no. It is not this. H divided by x times x plus h. No. Boop, boop. That's just wrong. All right? You don't get to pick who's the numerator of the fraction and who's the denominator, or where one fraction begins and one fraction ends. No. The whole thing, right, it was 3 divided by x plus h. That goes together. Even as I'm simplifying, that goes together. H is on its own. All right? Really just trying to bring that home, because I've just seen that error now 3 times on different students' papers. And so let's try and stop that. All right, so that, of course, the h's will cancel out there. And so our derivative, f prime of x, is going to be negative 3 divided by x times, oops, almost forgot to do one thing. Not quite yet, almost. Our derivative is still the limit as h approaches 0 of negative 3 divided by x times x plus h until we plug in the 0 for h. So let's plug that in now. F prime of x is equal to negative 3 divided by x times x plus 0. Right, and so our derivative, I'm just going to keep moving downward, our derivative is negative 3 divided by x squared. All right, so that is our derivative right there. Doop. I gave myself all this space, by the way, to find f prime of 2, which really doesn't really doesn't require me to use that much space. And I gave myself just a little bit of space for the derivative where I needed more space. All right, so now we have our derivative, f prime of 2, right, which would be negative 3 divided by 2 squared, which is negative 3 divided by 4. This is the slope of the secant line, or excuse me, the tangent line, the slope of the tangent line. It is our instantaneous rate of change at 2 something. We need the something, right? So to find the something, we got to plug back into the original equation, right? So let's find the something, right? So the y coordinate to go with our x coordinate. So f of 2, right? So we're just evaluating the original function. We just want to know what y value goes with 2, with x equal 2. All right, so we have, where's our function? 3 divided by x. So this would be 3 divided by 2. There's our y value. All right, so the instantaneous rate of change, the slope of the tangent line, when at 2 3/2 is equal to negative 3/4. Okay. If we want to know the equation of the tangent line at 2 3/2, what's the line? Right? What's the equation that represents that tangent line? All we have to do is plug into point slope form. Right? So just a little reminder, y minus y1 equals m times x minus x1. Of course, y1, x1, y1 is a point, and m is your slope. So we have y minus 3/2 equals negative 3/4 times x minus 2. Fine to leave it like that, although very common I'm seeing this. This is becoming more the trend, right? And so you'll see this more, I think, on the AP test. Just adding 3/2 to both sides and isolating y. Not rewriting it necessarily in a slope-intercept form, just isolating y. So y equals negative 3/4 x minus 2 plus 3/2. So I'm going to leave it like that, right? So we're not going to necessarily be simplifying the slope-intercept form, but we will isolate y. And there we go. There is the equation of the tangent line. All right. Let's try the next one. All right, so we want to find the equation of the line that's tangent to the graph of the function below at x equals 1. Right? So be a good idea. You see a cube there. Let's set up our equation, and then we'll talk about the cube. All right? So I'm just going to squeeze it up here. Remember our derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. H is in the denominator all by itself. Something else comes in the denominator, or if there, if what's in the numerator becomes a fraction, h is still in the denominator all by itself. All right, so now we're going to plug in x plus h for everywhere we see an x. Right? So we have the limit as h approaches 0 of x plus h cubed minus 6 times x plus h plus 2 minus, and use parentheses so you remember to distribute the negative, x cubed minus 6x plus 2, all divided by h. So now if you know the pattern to cube, you're going to be a lot happier when you have a problem where you have to cube. Then if you don't know the pattern, right, you don't really want to have to do this. I don't think you want to have to do that. Right? So all you have to do is remember the pattern in the exponents and just remember Pascal's triangle. Right? You don't have to remember a whole lot of it, but you should at least be able to cube and raise to the 4th power, right, without having to expand and square. All right, so we have the limit as h approaches 0. Right, so x plus h cubed. I'm going to kind of write out everything. Right? So let's just do the exponents, and then we'll add the coefficients. Right? So by the way, if there was a coefficient in front of x, when we expand with the exponents, you'd have to include that coefficient. But there's no coefficient, so we're not worrying about that now. Right? So the pattern for x plus plus for x plus something cubed, right? You're going to have the x. That's going to be to the maximum power, which is cubed. The other term in the binomial there is going to be to the minimum power, which is 0, right? Which means there's just going to be x cubed. And they're going to keep repeating that pattern. There's a plus there, so everything's going to be plus, right? So then you're going to have x squared. So that one goes down by 1. H comes up by 1. And then you're going to have x. And of course, h will be squared. And then you're going to have x now is to the 0 power. And now h is cubed. Right? So they're all there. They're just the x is going down in power, and the h is going up. The only thing we have to add is the coefficients. Right? So normally we won't write a 1, but I will here. I'll do that here. The coefficient there will be 1. Coefficient here is 3, 3, and 1. Right? That's the pattern in Pascal's triangle. That's what we would get if we actually expanded x plus h and multiplied it by x plus h, and then took our product and multiplied that by x plus h. Right? You'd have multiple x squared h's and x h squareds, right? From the different pairings of multiplying. Right? So if you can just remember the pattern, then you don't have to expand it. You can just write it. You don't have to really write the h to the 0. I'll just leave it there. Or I can rewrite it again. So this here, we'll just cross it out. This here actually would just be 1, right? So he's not going to actually be there. And then this one here would also just be 1, right? So x cubed, so all of this is really just x cubed, and all of this is really just h cubed, right? Just a little review on how to cube. We're taking all of that and we're subtracting x cubed minus plus 6x minus 2. And all of that is divided by h. All right, so now let's look at our terms here. I won't bother to rewrite that again. But actually what I might do is how about we just clean it up a little bit by getting rid of this and just making that an h cubed and an x cubed. Hopefully you got the pattern. And this was an h cubed. All right, so let's see if anybody is going to just cancel out, and we won't write them again. So there goes the x cubes. All right, and oh my goodness. Well, I'm able to write him. Who did we forget to write? Dum 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 dum. So focused on teaching how to cube, we can't forget him. Minus 6x minus h plus 2. Almost forgot him. Just focused on the cube part. Although I did remember the other half here. Minus x cubed plus 6x minus 2. All right, everyone see I just forgot to put him down until I stepped back and I looked and I say, hey, we're missing somebody. We're missing this part there. All right, so the x cubes are still canceled. And the 6x is canceled. And the 2 is canceled. And we're going to continue on now with the leftovers. Limit as h approaches 0. We've got a 3x squared h. We have a 3x h squared. We have an h cubed, all divided by h. Let's factor out the h. So we have, and silly me, f prime of x. You know, sometimes when you're really focused, you'll forget the little things. Then you look back and, oh, yeah, I forgot to write that in. But I certainly don't want to model bad notation. That wouldn't be a good idea. F prime of x, you just squeeze him in. Oops. Let me see if I can move this over a little bit. Oh, yes, I can. How about I'll write that a little bit nicer. Can't forget to tell everybody that this is the derivative. Right? And then finally, let's add it one more time. f prime of x equals, okay, now we'll continue on. All right, so f prime of x equals the limit as h approaches 0. All right, we're going to factor out the h, so this will be a 3x squared plus 3xh plus h squared, all divided by h. H will cancel. Now we can drop limit because we're going to plug in. So we have f prime of x equals 3x squared plus 3x times 0 plus 0 squared. All right, and so that's just going to leave the 3x squared. Right? Everybody else has dropped out. All right, and so that's our derivative. Let's find the slope. All right, so we're finding it at 1. F prime of 1 is 3 times 1 squared, so our slope is just 3. Right, so that's the slope of the tangent line. Right? It's also our instantaneous rate of change when x is 1. Now we just need the y-coordinate. Alright, so let's just plug it in up here because the equation's up here anyway. F of 1 is just going to be 1 cubed minus 6 times 1 plus 2. So f of 1 is 1 minus 6, negative 5, plus 2. So it's going to be negative 3. Right? Yes. All right, so we can just write our equation now. So we have y plus 3, right, because it's minus a negative, equals, my shadow keeps blocking me. I feel like I'm doing contortion act here. There we go, 3 is our slope. 3 times x minus 1. You can put that in slope-intercept form if you like. That's pretty easy enough, huh? Y equals 3x minus 3, and then we just add in a 3, or we can just move it over. Y equals 3 times x minus 1 minus 3. And simplify it, don't simplify it, either way is fine. All right, so we can just leave it like that, or if you want to put it in slope-intercept form, that's just going to be 3x minus 3 minus 3, so y equals 3x minus 6. All right, that's the equation of the tangent line. So I'll just put a big old tangent line here. And that's the tangent line only at the point 1, negative 3. Okay. Right, hopefully it's all making sense to you. Easy peasy lemon squeezy. Right? I mean, it looks like a lot of steps, but were any of them really complicated? Right? Maybe the cubing if you didn't remember the pattern, but now you do, right? And you're not going to be focused on telling somebody else how to cube, and you won't forget the minus 6h minus 6, minus 6x minus 6h. You won't forget that part. And if you do, you look back and you go, this doesn't look right, and you say, oh, I didn't write that one down, and you just write it down just like I did. No big deal. Right, so the derivative function allows you to calculate the instantaneous rate of change of a function at any point at which the function is defined. All you need to do is to evaluate the derivative function at the given point. Now there are times where your derivative is not defined. We'll talk about that later though. Right, so we want to determine, I think this is the last one I'm going to do, and then we're going to talk about, about function, about notation, and we'll do that in the next video. So a little preview of what's going to happen when we plug in, but ignore that for now. And so let's find the derivative of f of x equals the square root of x plus 2. All right? I don't know what those red marks are. All right, so we have the limit as h approaches 0, and that, of course, is our derivative. All right, so I just plug, I didn't write the equation on this, so I think we're okay without me writing it. We just plug in an x plus h for the x. All right, so that's going to be the square root of x plus h, and then there's plus 2. And then we're subtracting the square root of x plus h, all divided by, plus 2, all divided by h. Right? So now let's simplify that. We have our derivative is equal to the limit as h approaches 0. We have square root of x plus h plus 2. All right, so then minus square root of x minus 2, all divided by h. May as well simplify. F prime of x equals the limit as h approaches 0. So, of course, the 2's, they're going to cancel. So we have the square root of x plus h minus the square root of x, all divided by h. If we were to plug in 0, we would have square root of x minus the square root of x. That's 0. And we'd have 0 in the denominator. This is an indeterminate limit. And we learned what to do when we have an indeterminate limit with radicals. So rationalize the numerator. That's just the same as multiply by the conjugate. That's what rationalizes the numerator. Multiply by the conjugate. Right? Make sure you write that in, along with everything else. All right, so we'll just multiply, we'll multiply by the same thing with a little sign change there. All right, so our derivative is just the limit as h approaches 0. We have the square root of x plus h minus the square root of x, all divided by h, times square root of x plus h plus the square root of x, divided by square root of x plus h plus the square root of x. All right, so now we have f prime of x equals the limit as h approaches 0, square root of x plus h times the square root of x plus h. We're just multiplying here and distributing. That's, of course, just going to be x plus h without the square root sans the square root sign. All right, in the middle, our terms would drop out, right, because we would have a negative square root of x times x plus h and a positive square root of x times x plus h. So they would just, that would be a wash there. And then we would have negative square root of x times the square root of x. So that's going to be negative x because the square roots will cancel. All divided by, don't distribute, h times the square root of x plus h plus the square root of x. It will just make it worse. All right, so now let's simplify. Oh, look at that. The limits, the x's are going to cancel out. So f prime of x equals h divided by, the limit of h divided by, as limit of h approaches 0, of h divided by h times the square root of x plus h plus the square root of x. And now you see why I said don't distribute the h, because we're just going to cancel them out anyway. And there's our problem, right? There was what's causing the problem, that h, right? That's what gave us the indeterminate limit. A little reminder, you're going to keep, did that just move up? You're going to keep limit notation until you substitute, all right? Notation remains until the substitution occurs, right? Don't have a linkage error. So f prime of x is equal to, I'll rewrite it because I'm going to substitute now, is equal to 1 divided by, the limit, after I just said don't forget to leave the limit notation up, the limit as h approaches 0 of 1 divided by the square root of x plus h plus the square root of x. Let's just substitute now. And so we're going to have f prime of x is equal to 1 divided by square root of x plus 0 plus the square root of x. That's just going to be 1 divided by 2 square roots of x, right? That's just the square root of x plus the square root of x, which is 2 square roots of x. I'm fine with that. If you want to rationalize it, you can, right? And then you'd have the square root of x divided by 2x, right? But I'm fine with that. So there we have our That's our derivative, right? And that will, we use that to find the slope of the tangent line anywhere at all on this function. Wherever you want to find it, you can find it, right? You just plug in the value of x. Well, now, is this derivative defined everywhere? Let's just take a look at that derivative. Can you think of any value where you might have a problem if you plug it in for x? So, of course, we can't plug in 0. If we plug in 0, we get 1 over 2 times the square root of 0, which does not exist. You've got 1 divided by 0. So f prime of x is undefined at x equals 0. Now look at what it says above. Note that even though f of 0 equals 2, what does that mean? It tells us that the function, because f is the function, so the function is defined at 0, right? Because the function was, let's go back to the original equation. The function was just the square root of x plus 2. All right, so f of 0 would just be, I'll just put the function here. So f of x is the square root of x, and the 2 was not under the radical. Square root of x plus 2. And then if we plug in, we have the square root of 0 plus 2, and that's just 2. So that function is defined at 0. There's no problem at all. 0 is part of that function. However, the derivative is not defined at x equals 0, right? As you can see right here, we have a 0 in the denominator. So the y, you see the y here? The y is actually not referring to the fact that there's a 0 in the denominator so much as what's occurring in the derivative that causes us here to have a problem with the point 0 for the derivative. And so actually, because you can graph the derivative is a function itself. We'll learn some reasons why derivatives fail to exist in a later lesson, right? So y, we can see we have a 0 in the denominator right now. But we're going to learn a lot more about that, so stay tuned for more. And that's where I'm going to end this podcast. All right, next podcast we'll look at notation, and we'll also be solving some more problems using the limit definition of the derivative. Thanks for watching, and bye for now.